Hi, everybody, and welcome to the 7th episode of the AutoML series. I will start by saying a few logistical things. We'll be collecting and aggregating questions for Ryan throughout the talk, and we'll pick a few of them for the Q&A at the end. And by means of introduction, Professor Ryan Adams is interested in machine learning, artificial intelligence, and computational statistics with applications across science and engineering. He has broad interests, but often works on probabilistic methods and approximate Bayesian inference. Ryan is the director of the undergraduate certificate in statistics and machine learning. He co-founded WetLab, which was sold to Twitter in 2015, and formerly co-hosted the Talking Machines podcast. Ryan was faculty at Harvard from 2011 to 2016, was at Twitter and then Google Brain before joining the faculty at Princeton in 2018. He calls his group the Laboratory for Intelligent Probabilistic Systems. On a personal note, Ryan's paper on practical Bayesian optimization of machine learning algorithms with Jasper Znok, Hugo Rochelle, and later the paper with Kevin Sorksy and Jasper Znok on freestyle Bayesian optimization got me really interested into the field, got me kind of started in the field, and heavily influenced my thinking to this day. So without further ado, let's hear Ryan's talk.
My name is Ryan Adams, and I'm going to be talking today about some work that we've been doing recently on thinking about how to optimize expensive optimization problems where we're going to be using randomness in order to get gradients. And this is work with some fantastic students, Alex and Deniz, Josh and Nick. So this being the AutoML series, I thought I would sort of start by talking a little bit about my sort of personal trajectory in AutoML and how this kind of relates to the topics I'm going to talk about today. So I first started thinking about this kind of thing, I don't know, I guess about 10 years ago now, in the context of how to select hyperparameters for complicated machine learning models. And this is interesting because it, of course, helps us automate the process of building machine learning systems. But it also is representative of an interesting kind of optimization problem in which it's very expensive to evaluate the function pointwise. And the fact that it's expensive to evaluate motivates different kinds of optimization methods than we use in a lot of other contexts. In particular, got me excited about the ideas of Bayesian optimization. Now, over the intervening years, a lot of people have been excited about the kind of AutoML space, and it's evolved from simplistic views on thinking about machine learning hyperparameters into really thinking about architectures and lots of other aspects of machine learning models. And so it's evolved from something that looks like a sort of a pure optimization problem into something that I really feel like looks like design. And I find the sort of machine learning view on design to be a really exciting thing. And for me personally, this sort of trajectory starting with AutoML ideas has gotten me into a lot of other kinds of things that look less and less like machine learning and more like machine learning driven design. And so that's included collaborations on things like designing new kinds of proteins, designing new kinds of molecules for things like organic LEDs and organic photovoltaics, as well as thinking about how to design special purpose pieces of hardware for different situations. So these share a lot with the AutoML type problem, in that in all of these cases, we're trying to reason about some combination of challenging structured discrete spaces, as well as possibly complicated continuous spaces, and at the same time trying to evaluate any one of these designs as something that might be very expensive. And then even more recently, I've become quite excited about the idea of really thinking about all kinds of different design in this context, and in particular, mechanical design. And so that's involves things like thinking about how we can integrate machine learning systems with things like PDE-constrained optimization of finite element models, thinking about how we can design new kinds of mechanical metamaterials that have nonlinear behaviors that you wouldn't be able to see in natural kinds of materials, as well as thinking about how we can integrate machine learning and generative models with more traditional computer-aided design. And so to me, these are all kind of parts of a larger agenda of thinking about how to invent new kinds of things, whether they're machine learning architectures or mechanical systems using machine learning tools. Now, these kinds of problems, when I talk about them being expensive, that means a few different kinds of things. And it just boils down to the idea that these kinds of functions are frustrating along several different dimensions. So I mentioned that they might be expensive to evaluate, but it also might mean that the function itself is noisy whenever you try to evaluate at some point. It often means that gradients are not available, so the typical geometric information that we'd like to use to do optimization might not be available for us. They're almost always non-convex and difficult to reason about. And as I said, they often exhibit interesting and complicated discrete structure. Now, for a long time, the way that I've thought about this kind of problem and the way that a lot of folks have thought about it has been in the context of a probabilistic surrogate model, in which we deal with the complexity and the expense of evaluating the function, building a probabilistic model, and then reasoning about that surrogate probabilistic model instead of directly on the function. The idea being that it helps us make sort of new and the idea being that it helps us make interesting decisions about new designs to evaluate and new places to go that somehow give us high value relative to maybe more naive decisions that we might make in other kinds of problems. But actually, today, I'm not going to talk about surrogate-based models. I'm going to talk about actually a different view on this. I'm going to talk about trying to get gradients of expensive objective functions. So the Bayesian optimization story and the surrogate story often depends a lot on it being difficult to reason directly about the geometry. That is, things like gradients and curvature information. It being very difficult to reason about that kind of stuff directly, and instead we build a model. Here, in this talk, I'm going to talk about two different strategies actually for getting gradients that we can then use in service of expensive optimization problems. And so this is two different papers, kind of with a similar flavor of using randomness for gradients, but with different kinds of setups. So the first part, I'm going to talk about efficient optimization of loops and limits with randomized telescoping sums. This was at a recent ICML, and the student who did the majority of this work is named Alex Beatson. So a lot of the kinds of functions we're talking about, whether these are in AutoML or whether they're in PDE constrained optimization, a lot of the kinds of objectives that we want to solve have the property that they're a limit. That is to say that there's some function that as we turn some knob, here denoted n, and that knob sort of goes off to infinity, that the function becomes more and more precise. That is to say that we might have some discretization or some optimization, and what we really want to reason about is the infinite limit of that optimization or that discretization. And so what we want to do is reason about some set of parameters. Here I'm denoting these as omega, and these omegas govern sequence of functions whose convergence we care about. So this kind of optimization problem turns out to come up quite a lot in a variety of situations. So in the AutoML type context, it might be the case that f of n is representing the inner loop of a training procedure, where n is, say, the number of iterations that you're running for that inner loop. But there's also a lot of other kinds of things that have this flavor. So you might think about the inverse step size of something like an integrator for an ordinary differential equation. So as you increase n, then the discretization that you're performing in time is becoming finer and finer. Similarly, we might have spatial versions of that, or other kinds of situations in which we're doing finite elements of a set of partial differential equations. And again, we want that discretization to become finer and finer. But in machine learning context, it could also be things like the number of steps that we're training over for recurrent neural networks. So we'd like to run it on very, very, very long training sequences, but and so we might want to think of the training objective for an RNN as being in the limit of the length of these sequences. Or more generally, we might think of this kind of optimization as optimizing the fixed point of some fixed point iteration, in which we don't want to stop at some intermediate point. We want to run it all the way to convergence, and strictly speaking, that might sort of take an infinite amount of time. And so what I'm going to tell you about is a way to tackle these kinds of problems where you're able to perform training, able to perform optimization as though you're reaching that infinite limit and not truncating at some finite n. And so there's really one main trick, and to be clear, we didn't invent this trick, but it's a really nice one to know about, which is that we can take a limit like this and we can rewrite it as what's called a telescoping sum. So all I've done here is started with f0, and then I'm adding to that this infinite sum of the differences between each entry and the previous entry. So inside the sum here, it's fn minus 1. And so what happens is, if you were to write out this sum, then you would have these sort of alternating cancellations. And so after you cancel these out to infinity, eventually the value you would be left with is just fn by itself. So really, this is just kind of a notational trick for thinking about a different way to write down a limit. What's going to be cool here is that when we have things that look like sums instead of limits, then it's possible to form interesting randomized estimators. And so things that are defined in terms of limits, it might be possible to use different kinds of tools from stochastic optimization to actually handle sort of f infinity rather than fn for some finite n. So we call this thing a randomized telescoping sum, or a randomized telescope. And in its general form, the idea is that we have some sequence, and it could be the case that it's just converging to some finite limit, but in general, h could be infinite. And what we're going to do is write out that telescoping sum as the sum of a sequence of deltas, where the deltas here are just summarizing the thing that was on the previous slide. So there, at first, it's just the first entry, and then each successive entry is just the difference between this one and the one that came before. Then what we're going to do is put a proposal distribution on the integers. So we're going to pick some integer from a proposal distribution Q, and we're going to jump, in some sense, to that entry in the series. And then we're going to weight all of the entries with a weighting function W before we get to that capital N. So capital N is this random integer that we select from the proposal distribution Q, and then we're defining a weighting function W that satisfies this condition that its expectation needs to equal 1. And it turns out that if you do that, and you form the estimator that is the weighted sum of deltas for a random n, then this is an unbiased estimator of the limit. Now, this seems like kind of a weird thing, right? Because we never actually are able to get to that limit with some finite amount of computation, but with a finite expected amount of computation, we can nevertheless get an unbiased estimate of the infinite limit. And so we just have to come up with some proposal distribution Q and some weighting function that satisfies this condition. Now, that might seem like kind of a weird set of conditions, but it's a particular case, or it's actually a generalization, I should say, of ideas that you're probably already familiar with, in particular ideas like importance sampling. So one example of a weighting function is where you draw some integer n from this Q distribution, and then what you do is you weight your weight function is just the indicator function at that value n. And then when you do that, that unbiased estimator will just be taking essentially just importance sampling that telescoping sum and give you an unbiased estimate of the limit. And so to illustrate that, I'm going to give you a kind of a toy example. So, of course, for hundreds of years, people have come up with all kinds of clever ways to estimate pi, and some of those are fun ways to estimate pi as in stochastic ways. And this isn't a practical thing to do, but I think it kind of illustrates the idea here. So what we're going to do is use this telescoping sum trick to think about how to estimate pi as the limit of areas of regular polygons. So if you imagine that we could edit for any given size of a regular polygon, we could estimate its area, and we start with triangles and then squares and then pentagons and so on, then as the number of sides goes to infinity, then we would be able to recover pi from that area. So it's kind of a toy problem, but it's nice to as a thing to do to see this limit in practice. So if we were to imagine this sequence of polygons, then we might get two figures like we have on the left here. So the top figure is area as a function of the number of sides of the polygon. So the x-axis in both these figures is the number of sides. And of course, the area goes up and up and up. And as you go to the right, it converges to pi, right? As this thing converges to, as these polygons converge to a circle. And we can also look at the deltas of that, and that's shown here on the bottom. So the top is the limit that we care about, and the bottom is this sequence of deltas between each entry in the blue dots on the top. And so what we would do if we were to importance sample this series to use this trick is we would be drawing a number of sides randomly. So we would have some distribution on the number of sides in the polygon. We would draw one of those integers randomly, and then we would look at the difference in areas between that polygon and the one immediately before it. And that's what I'm showing here on the upper right is a randomly chosen polygon, one with one more side than that, and then looking at the difference between their areas. And on the bottom right, I'm showing a histogram that we would generate if we kept doing this. So we could do it again, draw another polygon, look at the difference in area between it and its neighbor, and that gives us, again, when we reweight that, an estimate of pi. And this is a thing we can continue to do, drawing random polygons and looking at their differences. And what we'll see is if we keep running this like we would expect for an unbiased estimator, the mean of these things will eventually converge to pi. So again, I want to emphasize this is kind of a silly thing to do, but it's illustrating what the trick is. We're jumping out to some point in the series, and then we're looking at the difference between that value and its neighbor in the series. And then if we correct it with the importance sampling correction, then we get an unbiased estimate of where the series goes in the limit, right? So even though this thing is always generating polygons with a finite number of sides, we're still reasoning about it as though we were looking at the infinite limit. And so you can see this histogram as we build it up converges to something that's going to be close to pi. So that's one particular version of a weighting function that corresponds to things you've probably already heard of. But it turns out that this trick is more general and includes all kinds of sort of older ideas going back to, for example, von Neumann and Ulam, with procedures called, for example, Russian roulette. So whereas in importance sampling, you would jump out to some value n that you chose from your proposal distribution Q, and Russian roulette, you choose that n, but now you consider all of the points between 1 and that location n. So what you're doing now, you should think of, rather than jumping out to some location, you're performing instead a randomized truncation of this infinite series. So we truncate the series at n rather than choose some individual value. And the trick here is that we need to come up with the equivalent importance weighting that allows us to perform that truncation and still get the right unbiased estimate. But that's a thing that you can compute straightforwardly, and I'm showing it here in the upper right. It boils down to the idea that, of course, when we perform a random truncation, then elements early in the series tend to appear in most of the random series, and so we're going to need to downweight those whenever we compute the estimate. So what we're going to be doing here is, instead of jumping out to some individual element in the series, what we're going to be doing is jumping out to an element and then truncating the series at that point. So if you look at the bottom left, you can see rather than just one square being read, we have a whole series of squares being read with the size of them reflecting the weights that we're using when computing the sum. And so now a bunch of them are read, but the early ones are much smaller, and so those are being downweighted. And we can do the same kind of trick, again generating random truncated sums of these polygon areas, and we'll see the same kind of effect, that as we do this, then we have an unbiased estimator that will converge to pi. Same kind of idea, but just instead of a single sample, we're doing this what's called Russian roulette, where we're going through the series and then stopping at some random point. And unsurprisingly, there's a whole spectrum of possible estimators that live between these, depending on the proposal distribution Q that you choose and the weighting function W that you choose, subject to it satisfying that condition on the previous slide. So again, here we can see the Russian roulette estimator is going to converge to pi. So what's interesting about this is it allows us to do stochastic optimization for limiting objectives. That is to say that if you have some objective functions, whether it's, say, an AutoML problem or some kind of finite element model, generally what you want to do is reason about it in that limit. But of course, you don't have an infinite amount of computation to compute that objective directly. The good news is we're used to doing stochastic optimization all the time anyway. That is to say that in machine learning, we use SGD, stochastic gradient descent, and sort of its cousins all the time on many different problems. And so we're used to accommodating a situation where we have a noisy but unbiased gradient. And that's exactly what we're getting here. And so we're trading off essentially truncation bias against variance in this estimator. And so we can get overall finite variance then in this estimator if we have some geometrically, sort of a sufficiently quickly converging sequence that either means geometrically converging or sort of sufficiently fast polynomial convergence. And this isn't too surprising. It just means that when you draw that random point in the sequence, it needs to be the case that you tend to go out far enough to get a good estimate of the series. And the point here being that you can now optimize the limit rather than this truncated approximation. And Alex has developed some interesting ideas in the paper for actually adapting then the properties of that weighting procedure online. So rather than having to choose between like the single sample case or the Russian roulette case, letting the algorithm decide over the sequence of an optimization which of these makes more sense. And so you can check out the paper for more details on that. And really, I want to emphasize that this isn't like a magical thing. What we're really doing is trading off truncation bias against variance. So we're just, in a sense, choosing a different kind of error and getting unbiasedness as a byproduct. So let's look at a couple of empirical examples of kind of using this for different problems. So one toy kind of example, in a sense, is doing something like trying to do system identification of a classic ordinary differential equation system. So there's this sort of classic Latka-Volterra predator-prey model with some classic data here, looking at populations of lynxes and hares, and the idea here being that these two populations interact with each other in kind of complicated ways. As if the population of hares goes down, then the lynxes have fewer to eat, and so you get these kind of offset oscillations in the population. So this is a classic example of trying to reason about a system with an ordinary differential equation, and so we might have the problem of trying to estimate the A, B, C, and D here in such a system, and treating those as unknowns on which we might put a variational posterior approximation after seeing some data. And so we can treat this as a stochastic optimization problem where we're going to be faced with a decision about what discretization to select for integrating this ODE with time. And so rather than selecting some fixed discretization, we can instead randomize the discretization using this telescoping sum trick. And what we find is that it's possible to converge to a good estimate with fewer total gradient evaluations, because rather than choosing some kind of high fidelity discretization that's going to be good for many different steps of training, we can sometimes do inexpensive things, and so kind of be inexpensive on average while still having the right gradient. Similarly, we can solve an AutoML type problem with this tool. So in this kind of situation, we have some set of machine learning hyperparameters that we would like to tune using gradients, and we can get these so-called meta gradients via automatic differentiation, either using something like the adjoint method or backpropagating sort of all the way back through the training. And what we'd like to be able to do is talk about the gradient of the validation loss with respect to these high-level parameters like learning rate or L2 regularization or different kinds of things. The problem with this is that we have to decide how long we're going to run that inner loop when we're going to perform this sort of AutoML optimization. If we do short runs, then it's cheap and that's great, but we run the risk of encountering truncation bias. That is to say that we might wind up with quite bad learning rates because we tended to always stop early. On the other hand, if we choose really long runs in order to avoid that kind of bias, then this whole optimization procedure is going to be much more expensive. And there's a really nice paper examining this short horizon bias that Roger Gross's group put out a couple of years ago that I definitely recommend. So we might reasonably ask, can we do the telescoping sum trick here, where what we would do is at each sort of training loop, we would make a decision about some random number of iterations that we're going to run the inner loop for. And then the idea being that if we reweight those appropriately and continue randomizing, then the meta gradient, that is the gradient that we're using to determine these hyperparameters on the outer loop, is going to be unbiased. And so now we're going to be able to avoid, hopefully, both the short run truncation bias, but also be able to do things in expectation more cheaply than we would if we just ran them for very long runs. And empirically, this is what we find, that we're able to do less work in expectation while still converging to what we would consider sort of the right answer for determining these hyperparameters. Then as another example, you could imagine trying to do this for training on a sequence model. So when we build a recurrent neural network on something, say, like text data, of course, what we'd like to be able to do is run it on infinite strings of text, right? The idea being that we imagine sometimes very long strings that the content associated with very long strings is important. And so if we were to use short strings whenever we train our sequence model, that maybe we wouldn't learn as much as as we should. That is, we would be biased in our understanding because we're only looking at, say, short sentences or short strings of text. So here you might hope that by randomizing, we could avoid that bias without paying the big cost of running on very long sequences. And this is actually a negative result for the randomized telescoping estimator, because we see relatively little gain for this additional work. And it's a little unclear why exactly this is. One might wonder, for example, whether it just boils down to the fact that something like an LSTM actually isn't really capable of learning that much about very long range effects. But in any case, we didn't see a gain in this case on using either the Russian roulette or the single sample estimator for training an RNN. So that's an idea for trying to train complicated models where you have this kind of nested computation, what we sometimes call bi-level optimization. What I want to tell you about now is a different kind of idea on how to use randomization to get gradients in things like AutoML type contexts. And so we call this randomized automatic differentiation. So the starting point here is that I sort of view automatic differentiation as kind of the original AutoML. That is, there's a lot of different things that help us improve the tool chain for training things like deep neural networks. And of course, we tend to think about these design type problems around selection of hyperparameters and selection of architectures. But of course, the tools we use do a lot of things for us that that were maybe we had to do by hand even just like 10 or 15 years ago. And in particular, the things that they do for us is they allow us to imperatively define differentiable models and then get the gradients for those things essentially for free or with no additional human work. And so when you think about tools like TensorFlow or PyTorch or JAX, that's what these things are doing for you. They're allowing you to define an architecture and then automatically find its gradient. And so I thought I'd take a quick minute and talk about how these tools actually work and then talk about a new view on how to use them. So broadly speaking, what these tools like JAX do is that you give them a function that is sort of in general some vector function. Here I'm denoting this as f going from Rn to Rm. And what an automatic differentiation tool will do for you is it will give you code that computes the Jacobian of that function automatically. So you write code for f, and it gives you code back for the Jacobian of f without you having to do any additional work. And so this turns out to be a very powerful thing that we use in a lot of different contexts, and it can be extremely convenient. So one tool that came out of my group a few years ago is called AutoGrad, and this is an example of using it where you would in Python write down some function here, a kind of a manual implementation of the hyperbolic tangent function, and then you have this higher order function called, in this case, egrad, that consumes the tanh function handle and returns a new function that you can apply. And so that new function will compute the first derivative, say, of this tanh function. And what's fun is that it's closed under itself. So that means that you can call this grad function again on the grad function that you just got and compute arbitrary derivatives out to whatever order you desire. And so you can take some original function and then get access, essentially get a function handle that implements code for arbitrary derivatives that you might be interested in. The reason we like this in machine learning, and in particular deep learning, is because it lets us specify a feed-forward neural network or some possibly very complicated architecture in a kind of imperative way, where we just talk about the layers and we connect these layers together, and we come up with some differential loss function that we wrap around that, and then we point this at data and construct a single function that is going to implement that loss function as applied to data. And this is kind of the empirical risk minimization kind of setup in its most basic form, where we're going to have some weights and this function returns a score of how good those weights are. And what's fun about automatic differentiation is that we can get the gradients with respect to those weights without doing any additional work. So all we've had to do is specify things in a feed-forward way, write down this architecture imperatively, and we get the critical information, and particularly the code that we need to train it, essentially with no additional work at all. We just get these functions for free. So this is what automatic differentiation does for us, and this is why I kind of call it the original AutoML, right? We are able to, fairly indirectly specify what we want what we want, and we're able to get these gradients in order to train it. So how does this kind of thing work? Well, it turns out that we can think of automatic differentiation as summing along paths in a linearized computational graph. And so so I know we all sort of use automatic differentiation tools all the time, but it's worth taking a minute to understand exactly how they work. So on the left here is a simple function that's the composition of several different sort of elementary math functions. And we could talk about the computational graph that arises from executing that code, right? We would have some x1, x2 here shown at the bottom as vertices in a graph, and then we have this this directed graph going up until we get to the output f, and each of these intermediate vertices is is computing some intermediate value. And then the idea of the linearized computational graph is that we have a partial derivative associated with each with each edge in this graph. And this is the linearization around the point x1 and x2 that we evaluate this function at. And so we can think of the Jacobian, or in this case the gradient, as summing over the products, as essentially summing over paths in this graph. So you consider every single possible path between input and output, and you take the product of the edges along those paths, and that will give you the Jacobian. And really, this is not anything fancy. It's really just computing the chain rule that you're used to, and observing that this chain rule has a kind of a decomposition according to these paths on the linearized computational graph. So we can then think about how we might actually compute that sum efficiently. And in general, when we have some quantity like this, this looks really obnoxious. It's a big sum over a possibly combinatorically large set of things. But because it's on a graph, we might expect to be able to do something like dynamic programming to perform some interesting graph transformations that compute this efficiently. And indeed you can, and that's what automatic differentiation is all about. So one thing we might imagine doing is something where we would eliminate vertices as we go and sort of collapse out the vertices, something we would call vertex elimination. And if we do that, sort of starting at the back or starting at the bottom, I should say, at the inputs and moving forward, we can propagate forward and eliminate all of these interior vertices and sort of sum over their linearizations until we're just left with a graph that connects to outputs, and that graph being the sort of final Jacobian. And if we do this in topological order, that process of eliminating vertices is what we call forward mode automatic differentiation. But that's not, of course, the only way we could imagine doing things, right? We could also imagine doing things in reverse topological order and eliminating vertices starting at the output and moving backwards towards the input. And this is often a good idea if you start with a lot of inputs and go to an output. And so you just have, say, one output f here at the end, and then in this case, multiple inputs x1 and x2. And again, you can eliminate all the vertices going backwards here. And this is what we would call reverse mode automatic differentiation. And of course, this has another name in machine learning. This is backpropagation. But it turns out that backpropagation is just another name for reverse mode automatic differentiation. And in fact, backprop isn't even sort of an appropriate name for all of automatic differentiation. It's just this one particular idea of going in reverse topological order back through this graph. And one thing I want to note before we go on is that that I want you to remember that when we do backpropagation or reverse mode AD, that it's necessary for us to store all of the intermediate values as we go in order to be able to construct that linearized computational graph. And that's gonna come up again later. It's also worth pointing out that in general, these are just two extremes. That is, forward mode AD and reverse mode AD are just two particular schedules that you might choose for eliminating vertices in a linearized computational graph, and they're not necessarily the optimal ones. So this is actually an example due to Paul Hovland of a graph in which neither forward mode nor reverse mode actually has the smallest number of arithmetic operations. That there's another order in which you first eliminate B and then eliminate D and then A and then C, and so that's neither sort of purely topological or reverse topological, and it has fewer arithmetic operations than either end. In general, finding the optimal schedule for Jacobian accumulation turns out to be NP complete, but it's worth observing that there's nothing magical about reverse mode automatic differentiation. It's not necessarily the best idea, even if you are even if your function takes a vector and outputs a scalar, which is the sort of the common machine learning case. So these are very powerful tools. They have been around for a long time, and of course, they've had a huge impact on the way that we think about machine learning problems. And I would say that automatic differentiation is one of the key tools that's enabled the deep learning revolution and kind of everything that's going on in AI for the last couple of years. Now, AD has been around for a long time, and it's been studied in a lot of sort of different contexts. But I think it's worth observing that it grew out of sort of applied math, and a lot of the ideas in automatic differentiation have been in service of applied math type problems, like, for example, solving systems of partial differential equations and so on. And so one thing you kind of see in the automatic differentiation literature is that it's kind of proud of itself in a sense for being as exact as if you did the math by hand or with a symbolic differentiation tool, but much more potentially computational, but much cheaper computationally because it doesn't have so-called expression swell. But the key thing here being that we have viewed automatic differentiation as something that we use to get exact gradients. And this is in contrast to, for example, finite differences or numeric approximations to the gradients. But the thing is that this is baggage that we might not feel like we need to carry around in machine learning, right? We use stochastic optimization all the time, where rather than being in the situation like on the top right here, where we're performing some kind of adjoint sensitivity analysis to get a detailed understanding of our fluid dynamics model, instead, what we're doing is taking sort of drunken walks in parameter space using noisy gradients. So we're optimizing with something kind of like we have in the bottom right here. And so you might reasonably wonder, well, why are we paying all of this computational cost to get exact gradients like we would in these other settings, if all we're going to do is introduce noise and do stochastic optimization anyway? And so that's what the kind of randomized automatic differentiation story is about, is rethinking autodiff in service of stochastic optimization, where we really don't need exact gradients. And so if we go back to that Bauer sum, we could think about how we might at least sort of naively form a Monte Carlo estimator of the Jacobian, right? So we're happy as long as we have things, as long as we have unbiased gradients for SGD, just like we wanted in the first half of the talk. But anytime we see a sum like we have here in the Bauer sum representation of the chain rule, then we might wonder if we could subsample that sum in order to get an interesting and unbiased estimate of the result. And so if we have some simple graph like we have here on the bottom, you could imagine sampling like one path at a time. And then if you upweight that in kind of the right way, then you would get an unbiased estimate of the sum of all three chains. And so this is a kind of a natural idea, right, for thinking about how you might construct such an unbiased estimate of a Jacobian. The problem is that for sort of most of the neural network architectures that we care about that have things like fully connected layers, the number of paths is exponentially large in the depth of the neural network. And when we have an exponential number of paths, then we would expect that in general, we're going to have very high variance for such an estimator. And that's going to mean that the naive path sampling that we might want to do is going to be infeasible for sort of practical problems. And unsurprisingly, instead, what we're going to need to do is find ways to take advantage of problem structure that exists in a lot of neural network architectures and take advantage of that to sort of come up with randomization schemes. And so one immediate thing you might think of is that I presented everything as I presented all these computational graphs as though the vertices were representing scalars, sort of individual floating point numbers. But of course, we don't think about that usually as the way we construct these things. We usually think of the vertices as you would usually think of the vertices as having vectors in them. And then when we multiply these things together, we're using matrices for the edges between them. And so if we were to take that point of view, then this graph on top, rather than being an exponential number of paths, would collapse into just a chain where the vertices are vectors, and the overall Jacobian is just the product of a sequence of Jacobians. So it turns out that that's actually an appealing view that allows us to import some fun ideas about sketching and sort of random projections from other areas of computer science. And in particular, if we think about that sequence of matrices that we're multiplying together to get the overall Jacobian, what we could imagine doing is injecting random matrices between those. So here I've got a PA, a PB, and a PC. Imagine that those are random matrices such that their expectation is the identity. And let's also further say that they're independent. Then what's going to happen is that when I introduce those, I get a randomized estimator of the overall Jacobian, but it's an unbiased estimate of the true product, right? And so this is just because I'm taking advantage of the independence in so that the product is sort of the product of the expectations. And then by having the expectation of each individual matrix be identity, then it's preserving the overall quantity. And so you can think of this, you can think of kind of a possible design space of random matrices P that satisfy this, that would include interesting things like subsampling and low dimensional projection, and allow you to do what is in effect this kind of path sampling, but without actually having to reason about dropping individual paths from this, from the overall computational graph. And so one way to kind of visualize that is to take something like a cartoon here of a convolutional neural network, and then imagine that what we're going to be doing is essentially constructing Ps that allow us to subsample the activations that we would otherwise use to compute these to compute the Jacobian of the overall loss. It's also worth pointing out that this view allows us to understand mini-batch sampling, that is the thing that we already do all the time, as a special case of this path sampling. So if you think about the overall loss function that you would compute for, that is the sort of full batch loss function summing over all of the data in your data set, the stochastic gradient descent that we usually use is essentially subsampling paths to the parameters from all of those data that go into the loss function. That is to say, kind of what we're used to is just taking one or a small set of the data, computing the loss just on that subset, and as long as we sample the subsets of data in a reasonable way, we get this unbiased estimate. Well, we can now understand that to just be a particular choice of what kind of paths I'm going to consider, and a particular randomization scheme. And so you can think of this randomized AD idea as generalizing even the thing that we're already sort of used to doing with mini batches. So what you might hope to get is different kinds of computational savings, of course, by doing this, by computing smaller amounts of the graph. And here we focus, though, on thinking about memory. So earlier on, I talked about how when we do reverse mode autodiff, that is when we do backpropagation, we need to keep around all of the intermediate states as we go forward, so that when we perform that reverse pass, then we can compute the adjoints we need in order to perform that Jacobian accumulation. So one might hope that with interesting sort of random projections and subsampling the paths, that it would be possible to get large reductions in memory usage by keeping less of the graph as we go forward, and then just performing sort of backprop on that subgraph. And so what we did here was a set of experiments to try to evaluate whether or not that's true by comparing to the sort of naive version of achieving memory savings, which is to use a much smaller batch size. So here the trade-off is to try to ask for a fixed amount of memory. If I could choose between doing randomized autodiff to get a smaller amount of memory, or I could choose to just reduce the amount of data that I use in each update. And then, of course, even within the randomized autodiff approach, we could also think about randomizing the graph overall for all of the data together, or we could think about a random graph per example. And so this is comparing these sort of different strategies. And what we see is that doing the randomization does give us an advantage over reducing the batch size. And what this kind of boils down to is that essentially it's able to see more data per step because it's able to have a larger batch size at the same memory cost, and that there's some amount of redundance that we would expect to have within each data example. So by having more data and just getting a little bit sort of less signal from each one, that on balance is a better use of the memory than just reducing the batch size. So machine learning problems are only one example of places where we use automatic differentiation. We use autodiff in lots of different kinds of scientific problems, and in particular, it comes up in the area of PD constrained optimization. So here's an example of a PD constrained optimization problem. The idea here is that there's some PDE that we want to, and we want to reason about its solution. Now, the solution is the thing that we only get after solving the PD numerically, and what we kind of like to be able to do, for lack of a better way to put it, is to sort of backprop through the solution back into the original parameters and try to find parameters. We could kind of think of these as designs of an abstract, in this case, fission reactor. We want to try to identify parameters for that are going to result in the target solution. And so we call this PD constrained optimization because we're trying to find parameters that we're trying to optimize parameters, but we have to live with the physics of the situation as represented by the PDE. And so we could treat this as a stochastic optimization problem in which we're going to need to sort of work backwards through the solution of this time step PDE solver. And here, just like in the cases we looked at a few minutes ago, it turns out that it's possible to do subsampling and still find good solutions for the overall problem. And this maybe isn't so surprising because you would typically, the idea of a typically what we express with a PDE is the idea that we want some kind of smoothness in the solution. And so you would expect to be able to drop areas of that solution and still retain kind of all of the same information. And here what we see is it's possible to perform this PDE constrained optimization, still find good solutions, but use sort of 99% less memory when we're doing that. This work, I should say, is in collaboration with folks at the Princeton Plasma Physics Lab. So I've talked about a couple different pieces of work here. I've talked about two sort of different views on how to get gradients in expensive optimization problems. In one case, thinking about bi-level sort of optimization problems such as come up in things in different kinds of AutoML contexts. And I've also talked about how we might rethink automatic differentiation in complicated systems to give us less expensive gradients of linearized computational graphs. So the takeaways overall here are that I feel like AutoML, at least for me personally, has grown from thinking about how to optimize a set of hyperparameters into really thinking about how do we automate a process of design under some kind of rational fitness function. And I think there's a large amount of interdisciplinary opportunities for this kind of thing where we use machine learning models and think about randomization, stochastic optimization, and bring these things to bear on problems in other kinds of engineering and scientific disciplines. And one of the things we like about this is that very often these wind up being the kinds of expensive optimization problems that really warrant interesting innovation in probabilistic modeling and things like Gaussian processes and Bayesian optimization. Here, of course, what we would really like to be able to do is use gradients. That is, take advantage of geometry whenever we can. And so part of this agenda is to try to find situations where we can compute gradients that would otherwise be unavailable to us. And I think it's worth spending energy to be creative in figuring out how to come up with those kinds of gradients. Put another way, I think one of the sort of superpowers in a sense of the machine learning community is a willingness to just live with stochastic optimization. That is to say that we're just used to having noisy gradients and solving problems using noisy gradients. And so we might think about situations that where people haven't usually used noisy gradients and think about whether stochastic optimization gives us some interesting mileage in solving those kinds of problems. So thank you all for listening, and I'd just like to highlight again the fantastic students who've done this work: Alex Beatson, Deniz Oktay, Joshua Aduol, and Nick McGreivy. Thank you again.
Awesome. Thank you so much for the talk, Ryan. It's super interesting. I mean, and super creative work in some sense because I completely didn't, as I was following it, I completely didn't see some of the things coming, which makes the talk super fun, but also really impactful work. And I don't know if you heard the introduction, but the introduction I was actually referring to some of your work, well, the practical Bayesian optimization work, but also the freestyle Bayesian optimization work. And I think one of the two figures in the first slide, I swear I didn't I didn't see your talk before making the intro. Was that from that paper? I think
it was. Yes, it was. Yeah.
And so it was super cool to see the first segment of your talk just go into kind of that direction as well. So I'm encouraging people to ask questions in the live Q&A. I will not have time to publish them, but please keep asking them. In the meanwhile, I have a backlog of questions. So the first one is around the first part, and the question is, could you comment on what kind of problems it might make sense for practitioners to trade off truncation error for variance?
Yeah, I mean, this is a great question, and in some ways, this is at the core of the, at the core of the idea. And what I'm not going to say is that there's some kind of like free lunch here, right? It's just a different kind of error, and and some days truncation error is what you want. That is in machine learning. Some days we live with bias, and some days we live with variance, and there are different reasons why we might like bias over variance or variance over bias. And this is kind of going all the way to the variance regime, when numeric methods traditionally have lived entirely within the kind of the bias regime. A situation that we find motivating is where you're really trying to perform optimization of a limit, and the kind of guarantees you would get for something like stochastic gradient descent would depend on biasness. And so then we're really optimizing that final limit and not some kind of intermediate thing where there would be a truncation level where our sort of gradients would send us the wrong direction. I should put an asterisk in that and say that what people do is they would sort of decay that they would sort of change the truncation level as they perform the optimization in order to avoid that kind of bias, but that would nevertheless cause you to have to do that tuning. So as much as anything else, it's kind of a taste thing. It's a different tool in the toolbox, and I think there are optimization problems where it makes sense, but it's not it's not so much a magic bullet. It's just a kind of a different way to think about error.
Awesome, thank you. I think a related question, in some sense, is: are there applications of randomized telescopic sums where the inner loop involves a physical experiment?
I love this question because I put together that little estimate of pi thing, which is obviously a ridiculous example. From a practical point of view, you would never do that. But it was tempting to sort of have my kids run this experiment and measure the area of different regular polygons in order to form this estimate in a physical way. And so you could imagine settings where, I feel like I could come up with settings where I would have a physical experiment that I was running at some sort of intermediate fidelity and trying to think about the limit of that. I don't have any sort of good immediate ideas, but I love the concept. Personally, I find the gradient aspect of this quite motivating, and that's a lot of the reason I'm interested in it. And usually we can't push gradients through physical experiments, and so so I haven't actually thought that hard, but I'm now fascinated by this idea.
Cool. I mean, it's hard to interact with the person who asked the question, given that it's kind of I get to be the medium. But I wonder if one way to do that would be to observe growth of some cultures, and if you could have a model that kind of character, right?
That's an amazing idea. Yeah, where you have some experiment that you'd like to run for sort of infinite time, and instead you make some intermediate observation or some long running physical system. That's a great point, right? That's a really fantastic point. Where as long as you could sort of convince yourself that you're seeing some variant of a limiting behavior, then you could imagine having many samples from that distribution and doing some randomized truncation. And as long as you're careful about when you stop watching, then you get an unbiased estimate. That's a great point. I had not thought about that kind of situation before. So thanks for bringing that up.
Awesome. So another issue that comes in biological experiments in particular is the batching. So you have a 96 well plate, so you cannot really do one experiment at a time in many cases. How can the work on on telescoping sums kind of address that? Because I know how to do that with a surrogate model. I know how to think about that in terms of an acquisition function and so on. But how would you think that could be addressed with your other work?
You mean so maybe you can explain a little bit more. So
yeah.
We're trying to run are we trying to perform optimization where I'm running batches? I'm able to run sort of 64 well plates, and I'm trying to optimize using a small number of such experiments. Is that kind of the way to think
so
about it?
exactly. You can only launch your experiment, so to speak, in batches of more than one. And so when you terminate something, you cannot terminate an individual sample within a batch, but you have to terminate the entire batch.
Oh, interesting. I think you could do that and make it correct at the cost of variance, because the correlation between the stopping times would hurt the variance but not change the mean. At least that's my gut reaction.
Awesome.
Just so I think it would probably hurt the value of doing 64 at a time, but not necessarily, but probably not change the answer as such.
That's great. I don't want to keep all the questions to myself. So with regards to the first half of the talk, could you please briefly touch upon the interplay, if any, of truncation error and search space size / cardinality? Would these methods scale to hyperparameter optimization with large complex search spaces and or neural architecture search?
Yeah, so that's a really great question. I think, you know, I don't want to regret saying that it will scale, but the way I think about this is that the sort of straw man is that you just do truncation. And if the only difference is where you put that truncation and how you make that decision, then I don't expect that it will actually sort of have a substantial a substantial impact on the scaling properties. That is to say, these search spaces are hard, and the way we do it now with truncation of training is, introduces a certain amount of error. And I think the real question is just whether or not randomized truncation creates more error than the alternative. And there, it of course depends on the details, but it really is just that, would I rather have bias or would I rather have variance kind of question. In both cases, if your gradient was going to be terrible before, it'll be terrible now too. But I don't think it kind of like, I don't think the problem structure really differentiates between these things. I think both of them are hard or both of them are easy, or not easy. I don't think any of them are ever easy. But I don't think it makes it worse, I guess I'll say, beyond the variance.
Great. You will have a community of NAS people now starting to investigate.
Yeah, who may cause me to eat my words, I guess. But
it's a voracious community in terms of new ideas. So there are probably 10 people implementing it. Cool. Actually, this question is related because, in some sense, no, I guess unrelated, but in my mind, related in some way. What happens when the so a lot of your of the promise of the first part of the talk is dealing with cost during optimization and allocating experimentation efficiently. One question that people had is what happens when cost depends on the hyperparameters themselves that you're optimizing. So in some sense, when it's a function of those hyperparameters, and maybe not a trivial function. Basically, something that is not necessarily super correlated with accuracy, let's say.
Yeah. So again, I would say that this is a real problem for sure that we're all sort of familiar with in the kind of hyperparameter optimization space, right? Where different choice of model size and different choice of learning rates and things like this might have a tremendous impact on the cost to actually run that experiment. And I would say that the like in the case where you're just performing truncation, you may have to wait longer. So in this case, that would be well, let me back up a second. One of the advantages I think you could talk yourself into here is that you have an opportunity for kind of multi-fidelity observations in, say, the Gaussian process that you're wrapping around it. One of the challenges that we saw in like FreeSaw and many other kinds of things in this space is that when you're running the training out and you get to some point and you're trying to guess, what's the final error going to be, you can either just take the current error as the final error, or you could try to build some model like we and other folks have done. One of the things that's kind of fun about randomizing is that you're going to say this is a noisy observation explicitly, and maybe if I do multiple of these, then I get some characterization of that variance, and you can actually talk about the variance explicitly versus kind of making up variance representing your uncertainty in this deterministic process. Mm-hmm. And so, I would hold out some hope that it actually creates opportunities for cleverness in that way, because you can reason about that variance explicitly and decide whether or not you'd like to run more experiments or run them deeper or adapt your proposal distribution. But I think the detail, the devil is in the details for something like this, and we haven't figured that, we haven't explored that yet. But I'm optimistic that there's like a space of clever things to do that give us some options that we don't currently have.
Awesome. I mean, it's really super interesting work. I definitely will chew on this for quite a while. Also, regarding to the second part of your talk, where we have more questions, but unfortunately we're out of time. With that, I wanted to thank you again for this incredible talk, and for joining us for the Q&A.
Oh, well, thanks for having me. It's a lot of fun to get to chat.
Thank you.
Bye.
And thank you everybody for attending. See you at the next one.